Okay, we want to continue in with the next part of our lecture on Chapter 2, the Copernican Revolution. In this lecture, we're going to talk about some of the physics that's relevant to astronomy, and a lot of that originated with the studies and the work of Isaac Newton. In particular, we want to look at Newton's 3 laws of motion and his law of universal gravitation. There are different ways that Newton's first law of motion are often expressed. Sometimes you'll see it written down as something like, an object at a state of rest will continue in its state of rest, and an object in a state of uniform motion will continue in that state of uniform motion unless acted upon by a net external force. That's a lot of words to remember, and it really is a little bit confusing, I think, to say it that way. So I have a different way of saying Newton's first law. The way I say it is written down here. To accelerate an object, one must apply a net external force. Now, in red here, I've written down what we mean when we say accelerate something. It means one of 3 things. It means we either speed it up, slow it down, or turn. And of course, it's possible to speed up and turn at the same time, or slow down and turn at the same time. But anytime you're doing any of these 3 things, speeding up, slowing down, or turning, that means you're accelerating. And in order to do that, you have to apply a force. The other thing you have to understand in order to understand this definition is what we mean by a net external force. The external force part is pretty obvious. If we're talking about an external force, that's a force acting on a body from some agent that's external to that body. And so the forces between atoms in a particular object, those are internal forces. Those are not going to affect the motion of the object. But if I grab that object and push on it, then I'm acting as an external agent applying a force to that body. So I'm applying an external force to that body. Now, if we want to talk about what we mean when we say the net part of this, what does it mean, a net external force or a net force? Let's consider a box where you have 2 people pushing on the box. One is pushing to the right with 10 pounds of force, and the other person is pushing to the left with 5 pounds of force. Obviously, the 10-pound force is the bigger force, it's going to win. And that box is going to go to the right. But it's going to go to the right as if it were being pushed by a single 5-pound force. That would be the net force because we've got 10 pounds in the positive direction and 5 pounds in the negative or the opposite direction. And so 10 minus 5 leaves you with 5 pounds, and that 5 pounds to the right would be the net force. Now, if I have a block and I'm pushing with 10 pounds from that way, and you're pushing with 10 pounds from the other way, what's the net force going to be? It's 0. And so that block is not going to slide. It's not going to accelerate at all. This box, if there's no other forces acting on it, if you have a net 5-pound force on that box, it's going to slide across the floor to the right. But over here, there's 0 net force, so it's not going to slide. This guy's not going to slide. This guy is. And so that's all we mean by the net force. If I've got multiple forces acting on something, the amount that wins, that's the net force. And of course, again, our whole point, we're talking about changing the motion of something. That's really what an acceleration is. It's a change in the state of an object's motion. Things want to keep whatever motion they have, and it takes a force to change their motion. This is kind of unintuitive. If I give a shove to a box and it slides across the floor, it's eventually going to slow down and stop. And so ancient people used to think that that meant to keep something going, you had to keep applying the force to it. But what they didn't recognize was that there was already a second force acting on that box. As it slides across the floor, there's friction with the floor that's slowing it down. If there were no friction, that box would keep sliding forever, or at least until it hit the wall or something, until it encountered something that applied a new force to it. If I go into outer space, far away from any planets or anything with gravity, and I throw a baseball off my ship, that baseball is going to continue in a straight line forever. It's never going to stop moving until it experiences a force, until it bounces off of something or runs into something or gets pulled on by some planet's gravity. It takes a force to change the motion of something. This was a huge insight that Newton made. And he explained it by saying this, simply, if you want to accelerate something, if you want to change the motion of something, that's what a force is needed for. Not to keep it moving, but to change how it's moving. So forces are necessary to change motion. And that's really what Newton's first law tells us. Again, to accelerate, that is, speed up, slow down, or turn an object, one must apply a net external force. That is Newton's first law of motion. Now, you may have learned it in high school or in some other class the traditional way, and I've got it here. I mentioned the traditional way of saying it. An object at rest will remain at rest, and an object moving in a straight line at constant speed will not change its motion unless a net external force acts on it. So here we see another sort of demonstration. I've got a ball that's just sitting here. It's going to sit there forever until what happens? Until someone comes and gives it a shove. And so you apply a force to that ball, you can change its motion. It was at rest, you apply a force, and then it's going to move. Now, if we pretend there's no friction with this table, that ball is going to just keep going across this table forever and ever. Now, if you want to turn it, that's another way that you can change the motion. And the way you make something turn is you push it from the side. And so if I push it in the same direction it's moving in this middle part B area, if I push it in the same direction it's moving, it's going to speed up. It'll go faster and faster. If I push it in the opposite direction, it'll slow down. It'll slow down and go slower. If I push it from the side, it's going to turn. But in each of those cases, speeding something up, slowing it down, or making it turn, you have to apply a force. When it's sitting here, if I want to speed it up, what do I have to do? I have to apply a force. It's that simple. So to change the motion of something, you have to apply a force. That's Newton's first law. Now, in this slide, we have Newton's other two laws, Newton's second law and Newton's third law. And really, the fancy words here tell us that when a force is exerted on an object, its acceleration is inversely proportional to its mass. And so you can see here's the formula. A is equal to the force divided by the mass. And so it goes as 1 over the mass. As the mass gets bigger, the acceleration gets smaller. Now it's also directly proportional to the force. As the force gets bigger, the acceleration gets bigger. And so I can write it out, and remember this A here stands for acceleration. What it tells us is that, so let's go back and think about the last slide. In the last slide, we looked at Newton's first law, which tells us in order to make something accelerate, you have to apply a force. And so I've got the force, and it gives me an acceleration, but how much is that acceleration going to be? Well, it depends on how big your force is. Obviously, if I make the force twice as big, I'm going to get twice the acceleration. But it also depends on the mass. And the bigger the mass, you're dividing by a bigger number, you get a smaller acceleration. So if I'm pushing on, my car is broken down on the side of the road and I got to push it over to the curb. If I push on it, I'm going to apply a force to my car and I'll get my car accelerated. I'll start it moving. Now, if I apply that same force to a semi-truck, it's not going to move as well as the car does because a semi-truck has a way bigger mass, and so the acceleration would be way smaller. It takes a much bigger force to accelerate a semi-truck than it does to accelerate a small car. Now, another way that we see this often written out is we say that the force is equal to the mass times the acceleration. And that's just from doing a little algebra on this formula here. We can rewrite it and solve for the force. Basically, if we multiply both sides by m, we end up with this formula turning into that formula. And so F equals to ma, force is equal to mass times acceleration. That is, force is equal to the mass times the acceleration, or acceleration is force divided by the mass. Either of those are ways of expressing Newton's second law of motion. And Newton's third law basically says when an object A exerts a force on object B, object B exerts an equal and opposite force on object A. What does that mean? Well, if I push against the wall with some force, the wall is also going to push back against me with an equal force in the opposite direction. That's why my hand, if I'm pushing against the wall, my hand doesn't go crashing through the wall, because the wall is pushing back with an equal and opposite force. And so nothing accelerates. The wall stops my hand by applying an equal and opposite force to it. It's the same idea if I'm standing on the ground. There's going to be a force due to my weight pushing me into the ground. And so my weight is pushing me into the ground. What's the force? What's the floor going to do? The floor is going to push back with an equal and opposite force. How do I know that's happening? Because I'm not accelerating downward. If the weight was if I step off of a ledge, I accelerate downward and I fall down below because gravity is pulling me down. And when you have a net force, you accelerate. But if there's an equal and opposite force from the floor, then you're not going to accelerate. And so that's how we know these forces have to balance. And that is what Newton's third law tells us. Now, there are a couple of things about Newton's third law that are worth mentioning, because there are certain aspects of it that are confusing to people sometimes when they encounter it for the first time. And so I want to just go over a couple of the common misconceptions that people have about Newton's third law. So here I've got a picture of a horse pulling a cart. Don't make fun of my horse. He already has self-esteem issues as it is. But the idea here is I've got a force from a horse on a cart, and it's going to pull that cart across the floor or across the ground. Now, some people might say, wait a minute. Newton's third law says for every force, there's an equal and opposite force. And so it seems like those forces should cancel, like we were talking about in the last slide. The forces should cancel. So how is it possible that the horse is able to pull a cart across the ground if for every force there's an equal and opposite force? And it's very subtle. The answer to this is very subtle. So let's think about what we're talking about. So I've got a force of the horse pulling on the cart. So I'll call that the force of the horse pulling on the cart. And there's going to be an equal and opposite force, and I'll call that the force of the cart pulling on the horse. And so I've got F with a little H/C up above. That tells me that's the force of the horse pulling on the cart. So the slash means on. And so here, down below, I've got the equal and opposite force of the cart pulling on the horse. And so why don't these forces cancel? And the answer is, yes, there are equal and opposite forces, but they're acting on different objects. So what is this force acting on? It's acting on the cart. What is this force acting on? This is the force of the cart on the horse. It's not acting on the cart. It's the cart acting on the horse. So this force is acting on the cart. That force is acting on the horse. So how do we know if the cart is going to move? Well, we don't care about what forces are on the horse. We look at the forces on the cart. Maybe there is some friction down here. Okay, the next thing that we want to look at is another thing that people kind of misunderstand about Newton's third law. Okay, so here I have a little car like a Volkswagen Bug, and it's going down the road pretty quickly, and there's another vehicle like an 18-wheeler, much bigger vehicle, that's going in the opposite direction, also going pretty quickly, and these two vehicles, they smash into one another, they collide, crash! The question is, which of these two vehicles gets the bigger force? Does the little Volkswagen Bug get the bigger force, or does the 18-wheeler get the bigger force? The answer is a little bit surprising for most people, because most people, they naturally think, oh, well, obviously it's the Volkswagen Bug that gets the bigger force. But that's not true. What does Newton's third law tell us? If I've got one thing pushing against another thing, that other thing is going to push back. How are those two forces going to compare? For every force, there's an equal and opposite reaction force. Those two forces are going to be equal and opposite to one another. Equal and opposite. That means that the little Volkswagen Bug and the 18-wheeler, when they collide together, they exert an equal force on one another. Equal but opposite, but equal in amount. Now that's very unintuitive, because like I said, most people would guess that the little Volkswagen Bug gets the bigger force. Why is that? Because if you think about it, you visualize what's going to happen in this collision. That little Volkswagen Bug is going to be knocked to hell and back. It's going to get clobbered. That 18-wheeler is barely even going to feel it. It's just going to keep on trucking. But this guy is going to get clobbered. So it makes sense that he would get the bigger force, right? Because he gets clobbered. But let's think about Newton's second law. A equals to F divided by M, the force divided by the mass. Now the force, we just said, the forces are going to be the same. The force from the collision, the force on the little Volkswagen Bug and the force on the 18-wheeler, they're going to be the same. What's different, though, is their acceleration. Because with the Bug, we're dividing by a much smaller mass, and so it gets a much bigger acceleration. Whereas with the 18-wheeler, we're dividing by a much bigger mass, and you get a much smaller acceleration. As the mass goes up, the acceleration is smaller. So these two guys, they collide with one another. They get the same force, but the Bug gets a huge acceleration in comparison, and so it looks like it gets knocked to hell and back because its acceleration is so much bigger. It's not the force that's bigger, it's the acceleration. And that's what when people get confused by these concepts, a lot of times they're not being really careful about how they're thinking about it, and they're mixing things up. They're mixing up a velocity with an acceleration or a force with an acceleration. And they're related to one another, obviously, but they're not the same things. That's why it's important that we understand these definitions, because that tells us what's actually going on physically in the world. The next thing that we want to talk about is gravity. Now, on the Earth, near the surface of the Earth, the acceleration of an object, that is how much it's going to speed up if you drop it, that is essentially constant. And it's always directed towards the center of the Earth. Now, if we're standing on the surface of the Earth, that means that the acceleration due to gravity is always going to be down. And so you can see, here's sort of the classic example. You throw a baseball or some kind of ball up, and the acceleration is going to be down. Now, remember what I told you. If the acceleration is opposite the way that something is moving, it's going to slow down. So I throw the ball up, it's moving upwards, but the acceleration is down, so the ball slows down. And then at the top, it's going to pause momentarily. It's going to stop at the top just for an instant. But that acceleration is still pulling down. And so what happens is the ball's motion reverses and it starts to fall down. And as it goes down, it goes faster and faster. You can see that the distance between each successive ball is a little bit bigger than the one before. Here, it's slowing down, and here it's speeding up. And so it slows down on the way up, it pauses at the top, and then it speeds up on the way down because that acceleration is constant and always pointing down. Now, just FYI, I'm not going to make you remember this number, but the rate at which the velocity changes is 9.8 meters per second every second. And so I've written that down here, that the acceleration, and there's a little g there for gravity, the acceleration of gravity is 9.8 meters per second every second. So if I go to the top of a tall building and I drop a ball off the top of the tall building, after 1 second, it's going to be going 9.8 meters per second. So I drop it, it's not moving. It's at rest when I drop it. It's got 0 meters per second, and then I let it fall from gravity. After 1 second, it's going to be moving 9.8 meters per second. After 2 seconds, it's going to be moving 19.6. That's twice as fast as this, 19.6 meters per second. The numbers are a little bit weird. Let's call this 10, because this is really, it's about 10 meters per second every second. That's the rate at which the velocity is changing. And so, again, if I drop it, I let it fall from rest out of my hand. After 1 second, it's going 10 meters per second. That's how much its velocity has changed. After 2 seconds, it's going 20. After 3 seconds, it's going 30 meters per second, etc. And just FYI, the way we normally write these units is we would say that's meters over seconds squared. And so if you ever see that, that's just a compact way of writing meters per second divided by seconds. Remember, acceleration is how velocity is changing. It's speeding up, it's slowing down. And so how fast is it speeding up or slowing down? It's 10 meters per second change in velocity every second. That's our acceleration. Now, if we're not talking about the surface of the Earth specifically, we might be talking about the gravity force between two asteroids, or between the Earth and the Moon, or the Earth and the Sun, or whatever. And so the sun and a comet, it could be any two objects that you want. There's actually a formula that tells you how much the force of gravity is. And the formula tells us that the gravitational force is proportional to the product of their masses, and then it's divided by the square of the distance between them. And when you have something that's proportional, the way that you make it into an equation is you have some sort of constant of proportionality. So putting it all together, this is the force of gravity between any two objects. We have the force of gravity is this special constant big G, the gravitational constant, times the product of the two masses. That's fancy math speak for you just multiply the two masses together, and then you divide it by the distance between the masses squared. And so, however many meters apart the masses are, you take that, you square it, and that's what you divide by. And this big G is 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. Oh, that all got jacked up. Let me fix that. There, so we have big G, the constant big G, is 6.67 times 10 to the minus 11 newtons times meters squared divided by kilograms squared. You don't need to memorize this or know it. That's just the value that big G is to make the units come out to be newtons. And so we want our force to be in the metric system version of force, newtons. And this is the formula for the gravity between any two masses. And we'll talk about this a little bit more in the lecture, but this is the basic idea. The next thing I want to talk about is satellites. And this picture that I'm drawing is actually a crappy version of a picture that Isaac Newton himself drew to explain how satellites work. And I remember learning this when I was a student and just thinking how cool it was. I mean, I really think this is a really cool thing, understanding how satellites work. You guys might have heard the story. They tell the story. Isaac Newton was sitting under an apple tree and an apple fell on his head and he discovered gravity. I remember hearing that story when I was a little kid, and even as a little kid, I recognized that story made no sense at all. What? Nobody ever saw an apple fall before Newton did? I mean, what does it mean he discovered gravity? Well, what that story is actually referring to was Newton was very interested in the motion of the planets, and particularly how the planets go around the sun, and also similarly how the moon goes around the earth. And he recognized that the force of gravity that pulls an apple from the tree down to the ground has to be the same force that keeps the moon going in a circle around the earth. And he figured out how that worked. And so he kind of drew this picture to explain it, and I'm going to try to draw my not so great version of it to kind of try to explain it to you. So imagine you're on the earth, and of course this is not to scale, but I've got a very tall tower, and I shoot a gun, and a bullet comes off the tower, and so what happens is the bullet's going to come down there, and it's going to land on the ground below the tower. And if I shoot the bullet faster, it's going to go further. But notice something. The further away it goes, it's actually being affected by the curvature of the planet. If it's going fast enough, this guy is actually falling down more of a height because this guy is actually blocked by the ground, but the ground is curving out from underneath it. What Newton recognized is if I drop an apple, it's going to fall a certain distance in a second. And if it's going horizontally, if the earth curves out from underneath that apple in the same amount of distance, then the apple will be the same height above the ground that it started with. And so this is the idea. If I shoot a bullet fast enough, what's going to happen is it's going to fall towards the center of the earth, but the earth is curving out from underneath it. And so if it's going fast enough, it'll keep the same height above the earth the whole trip. It's constantly being pulled towards the center of the earth. Everywhere in its path, it's being pulled by gravity towards the center of the earth. But the earth is curving out from underneath it. Think of it like this. If, the earth were flat, if the earth were completely flat, this bullet would come here, this bullet going faster, it would land the same way. And so if the earth were completely flat, no matter how fast I shot the bullet horizontally, it would come to the ground in the same amount of time. But because we know the earth's really not flat, it's actually curving out from underneath it, the earth is down below. For this guy which is shot faster, the earth is actually down below. And if the earth curves away the same distance that the bullet falls, then the bullet will be the same height above the earth. That's what we're talking about. And that's basically the way that satellites work, whether we're talking about communication satellites that are providing us with TV or the moon. Because the moon, yes, the moon is being pulled towards the center of the earth, but it's also got a sideways velocity, and it's going fast enough so that it actually just keeps falling around the earth and missing. That's how satellites work. But just like the apple from the tree pulled straight down, the moon is being pulled straight into the center of the earth. It's just because it's got this very fast sideways velocity, it goes around the earth instead of crashing into it. Now here we can see a much prettier version of that picture. And what we find, not only do we get this sort of circular satellite motion like I was talking about in the last slide, if you go a little bit faster than that, you actually will form an ellipse, kind of like Kepler's laws tell us. And so remember, a circle is just actually a special case of an ellipse. And the part where it's not going fast enough to go all the way around the earth, so I don't know if you can see on the slide here, but there's one that's like, it's just right there, and it's basically shot a little bit, and it makes an arc, and it lands on the earth. Well, you can see there's a dashed line of the ellipse that it would have followed if the earth weren't there. And so that is showing you sort of the Kepler's law type relationships that all of these have. Now, if I go fast enough, instead of falling around the earth, I'll actually break free of the gravity, and that's called the escape velocity. If I go fast enough, the Earth's gravity isn't strong enough to keep me falling around it, and I'll fly off. And so basically, this is the concept of escape velocity or escape speed. It's the speed necessary for a projectile to completely escape a planet's gravitational field. If you're going slower than the escape velocity, you'll either land on the planet or you'll go into orbit around it. Those are the two options.